Hello everyone, in this video, a special video, we are going to take a look at the possible locations for extraterrestrial life across, well, perhaps not the universe, as it is much too large to even remotely consider something like that, but we will take a look at our nearest neighborhood. The Earth, our home. As we are watching it rotating right now, it is difficult to imagine the whole biodiversity of all the species inhabiting this precious little planet orbiting our Sun. But is it the only place harboring life? Let's first see if our own solar system could have some hidden oases where life will be able to or could flourish. Odd as it may seem, we will start our excursion with the Moon. At the first glance, the Moon is inhospitable to life. It is a rocky body without sources of water, it has virtually no atmosphere and is very unlikely to have any organic chemistry, unless carried over to it by asteroids. And yet, perhaps you have heard about the tiny microanimals called the tardigrades. They are known to be some of the most resistant organisms living on the Earth, in almost any environment it has. What is the link between the tardigrades and the Moon, though? In 2019, Israel launched a flight to the Moon with a moon lander called Bereshit, or In the Beginning, which is the first word of the Torah and of the Bible. Said lander crash-landed onto the surface of the Moon. On board the lander, there were tardigrades maintained in a cryogenic state, so basically in suspended animation. We can only suspect whether these tiny beings survived the crash landing, but who knows, perhaps they remained dormant this 6 years later and could be an example of now extraterrestrial life quite close to home. Next comes another fairly close and superficially unlikely candidate for life, Venus. Although one of our two direct planetary neighbors is a victim of a runaway greenhouse effect, with temperatures on the surface far exceeding anything life as we know is able to withstand, and the atmosphere is full of noxious gases and fumes, there have been hypotheses claiming that perhaps life could still exist in microbial forms in the atmosphere. In 2019, a team of astronomers led by Yeon-Ju Lee speculated that long-term changes in the planet's albedo, or the reflectivity of light, could be the result of the presence of unknown absorbers, chemicals, or even possibly colonies of microbes in the upper atmosphere of Venus. In September 2020, Jane Greaves and her team from Cardiff in the UK announced the likely detection of phosphine in the Venusian atmosphere, which is a gas not formed by any known chemical processes on the surface of the planet itself. The discovery remains tentative though, and we will see what the future brings in terms of Venusian chemistry. The other cosmic neighbor, Mars, is not necessarily much better as a life candidate. While it does seem to have water frozen in its polar caps, the very thin atmosphere, which does not provide much of a shield against cosmic radiation, combined with surface bombardment by various objects, does not bode too well for possible life currently and potentially existing on the Red Planet. If present, life would have to exist under the surface. The only hints at the possibility of life are the detected methane and formaldehyde, simple organic compounds, although they can be a result of geological processes as well. The Chevaya Falls rock was discovered on Mars in June 2024 by the Perseverance rover exploring the Martian surface. It shows patterns which could be explained by the activity of microbial life, once possibly existing on the planet. Nevertheless, this is just one of multiple explanations for the rock and its properties thus far. Still, given its relative proximity to the Earth and the conditions which are harsh, but possibly manageable with the help of technology, Mars is currently the subject of speculations as humanity's possible first destination outside of the Earth. The gas giant planets are unlikely to have any forms of life given their distance from the Sun and thus low levels of energy received. However, it could be theoretically possible for life to exist deeper in their atmospheres, where pressures and temperatures are higher, and where compounds like liquid water and ammonia, so namely ingredients for life, could be present. The moons of the gas giants are a completely different story though. First and foremost we have Europa, one of the 4 classical moons of Jupiter. This moon is large, with its radius being 1/4 that of the Earth, and the moon is stable. While the surface of this moon is composed of rock, mainly silicates, measurements combined with its quite light color suggest that underneath the crust of the planet there is an ocean of liquid water. And oceans of liquid water, as we know, are the original location where life began on our planet. While definitely a speculation, it could be conceived that deep under the rocky surface there is a whole biosystem of its own, with organic material accumulated early on during Europa's formation. Really wide speculations speak of organisms as complex as our earthly cephalopods, possibly thriving deep in those oceans. This could be possible, as while the surface of Europa is cold, the effect of pressure acting on the sublunar ocean could potentially heat it up enough to reach temperatures hospitable for life. Such environs could operate similar to hydrothermal vents on the Earth, providing precious heat to whatever life forms could exist in Europa's oceans. One more thing of note regarding Europa is the far future of the solar system. In approximately 5 billion years from now, the Sun will exhaust its current main source of fuel, hydrogen in its core. Fighting to sustain energy production, our star will expand approximately 100-fold and ignite helium, providing a secondary energy source. This expansion will move the habitable zone of our solar system, so a region of space with temperatures high enough to maintain life, such as on Earth right now, much farther outwards. It seems that Europa will likely fall within the habitable zone in said distant future. In this case, the subsurface water, shielded by a cover of ice, could form an actual ocean covering the surface of the moon, offering a window of opportunity for life over a period of approximately 200 million years, and a possible shelter for our far future descendants. Similar speculations apply to another of the Galilean or classical moons of Jupiter, Ganymede. Similar to Europa, the studies of the magnetic field of this moon and its spectral analysis seem to have confirmed the presence of a subsurface ocean, very likely containing salt water, which could be similar to our own oceans. Various inorganic salts and possibly aldehydes, organic compounds, were detected on Ganymede's surface, once again prompting questions whether this could have been produced by life evolving quietly deep under the surface of this Jovian moon. Callisto is the last of the moons of Jupiter which could, at least theoretically, harbor life. Similar to its counterparts we have discussed, it is likely to have a subsurface ocean. The issue with Callisto, though, is the environment. The moon hosts high concentration of chlorides, possibly resulting in extremely high salinity of the water running deep within the moon. This in turn would limit any life existing there to the so-called halophiles, or beings adapted to extremely high concentrations of halogen salts, chlorides, bromides, and possibly iodides. As we keep on moving outwards through the solar system and away from the Sun, the temperatures keep dropping to levels which are difficult to consider from our everyday perspective. And yet, as the cold prevails, the possibilities for life are not exhausted by any means. Our next stop is Titan, the largest moon of Saturn. The question about possible life present on this Saturnian moon has been the subject of hot debates in the scientific community for a long time now. Let's see what is so special about Titan then. The first quite striking and perhaps even surprising feature of this moon is the fact that outside of the Earth, it is the only place in the solar system we know to have liquids flowing freely on its surface. There are actual rivers, lakes and seas present on Titan. Where things get quickly complicated, though, is that all those liquid bodies are not made of water. It is simply far too cold on the surface of Titan for liquid water to exist, with temperatures below 100 Kelvin, minus 180 degrees Celsius, or minus 290 degrees Fahrenheit. However, methane forms liquid under such conditions and is very likely to be main ingredient of all the liquid bodies observed on Titan. Moreover, Titan's atmosphere has been studied quite extensively and has been shown to contain nitrogen, methane, hydrogen, acetylene, ethane, hydrogen cyanide, benzene, toluene, and other organic compounds. Such a rich tapestry of organic chemistry provides a very promising basis for quite complex reactions. Those reactions need energy though, and it could be provided, for example, by asteroid impacts, opening brief windows of opportunity for complexity to emerge from this primal soup for some time. We should also notice the fact that Titan has quite a complex atmosphere, actually the second most complex one out of all rocky bodies in the solar system after the Earth, another factor which could promote life at some point in time. The expansion of the Sun we have mentioned while discussing Europa would affect Titan as well. Given the larger distance involved, the condition on this moon would not be as favorable as near Jupiter, but the temperature rising to approximately minus 70 degrees Celsius could allow for methane to be replaced with a liquid mixture of water and ammonia in the distant future, providing another medium favorable to the development of complex life. It is also speculated that the conditions could be good enough for our descendants to move here, should Europa prove to be inadequate to provide shelter for any reason. Similar to Jupiter, Saturn also has other moons with theoretical habitability. Enceladus is the first of those. This moon has large quantities of water present on it. As was the case with Europa, there is likely a massive subsurface ocean on this moon. It also shows geological activity with likely cryovolcanism, but instead of lava, the volcanoes on Enceladus eject ice. Such activity hints at the possibility of higher temperatures present deep within the moon's structure, which combined with the presence of water and low salinity could theoretically provide some space for simple life to evolve. The moon also has nitrogen, carbon dioxide, and traces of hydrocarbons in its atmosphere. Dione is a much weaker candidate for life, however, this moon of Saturn also shows the presence of large quantities of frozen water on the surface, and the possible subsurface ocean lurking deeper beneath. It is relatively less studied though, and there is much less certainty regarding other chemical ingredients required, or at least promoting the development of life. Our next potential source of life is located much further away, near the edge of what most people think of as the solar system. Triton, the largest moon of Neptune, has a thin atmosphere. Moreover, it has quite an active volcanic life, and plumes several kilometers in height have been observed, composed of water and nitrogen ice. The presence of those compounds of polar caps made of frozen nitrogen and methane shows the presence of the most commonly listed and most basic ingredients required for life as we know it to evolve. The main obstacle for any life on Triton would be its enormous distance from the Sun, just over 4.5 billion kilometers, resulting in surface temperature on Triton of minus 235 degrees Celsius, just 40 degrees Celsius or 70-ish degrees Fahrenheit above absolute zero. Yet life always seems to find a way, and who knows what we could find deep under the surface of this Neptunian moon. There are other objects existing in the solar system which are possibly worth mentioning. While the chances of life existing there are much smaller than where we mentioned before, we have the dwarf planet Ceres, which has the higher percentage of water than any other body in the solar system except the Earth. It has a very delicate atmosphere and is still close enough to the Sun to possibly include liquid water as a subsurface reservoir. The so-called trans-Neptunian dwarf planets, Pluto being the best known of them, often host quite substantial quantities of frozen water, ammonia and methane, and some exhibit cryovolcanic activity. Unfortunately, the issue with them, just like with Triton, is their enormous distance from the Sun and low temperatures. These issues are further exacerbated in some cases by irregular orbits, which vary the amount of heat reaching those bodies and diminishing any chances for even microbial life to develop on them. While part 1 of the video was dedicated to the exploration of our own solar system and places where life could thrive, we will now do the same but looking outwards. Before we go into details, let's think about the scales here. The observable part of the universe alone can contain up to the estimated number of 2 trillion galaxies, and thus 10 to the power of 24 of stars. The universe as a whole can be inconceivably larger still. Thus, it is literally impossible to ascertain the number of possibly habitable planets. We cannot even do the same for anything else than our own galaxy Milky Way, and even that task would be immensely difficult, as the galaxy contains anywhere between 100 and 200 billion stars, most likely. Thus, we are going to focus on the closest neighborhood of the Sun, and some places which may be promising in regards to life. Before we do that though, we should first consider the type of stellar systems which can harbor life at all. To do that, we have to take a look at the so-called stellar classification, which we can now see on the screen. The hottest and some of the biggest stars fall into the O and B types, which are blue and bluish stars. Due to their temperature and short lifespans dictated by the enormous rate at which they burn their nuclear fuel, they are not very likely to be capable of hosting life. A-type stars could theoretically host life, despite the fact that their lifespans are much shorter than that of the Sun. However, one of the issues here would be the higher share of UV radiation emitted by such stars, and this radiation poses the risks of mutation and is generally harmful to many living organisms. The G-type stars are called yellow dwarfs, and our own Sun lies in this category. Their lifespans, ranging from a few to perhaps 20 billion years, leave quite a lot of time for life to develop, with parameters similar to our star. This makes them promising candidates for life. K-type orange stars are smaller and burn longer than the Sun, which also renders them suitable for even intelligent life to emerge. The one drawback here is the smaller amount of heat and light emitted. The M-type red stars live the longest, but they often show some unpredictable events like flares and other radiation anomalies which could easily disrupt life, atmospheres, ionospheres on planets, and so on. Below the stars and above the planets, we have three stellar types of L, T, and Y, the so-called brown dwarfs or failed stars. The hottest of them reach 1,000 or so degrees Celsius, while the coldest white dwarfs have about the same temperatures as our Earth. This could make such objects sources of warmth, which would be adequate enough for some more exotic life, not so dependent on light as our own diverse biosphere, which could exist around brown dwarfs. Still, G and K-type stars are usually the main targets of search for extraterrestrial life on planets around them, as they offer conditions similar enough to our own, the only certain and confirmed type of life we know. Our search begins right next door in terms of our stellar neighborhood, the triple star system of Alpha and Proxima Centauri. Now, a triple star system seems like a very unlikely place for life to develop, as such systems involve three stars influencing a planet, but in this case luck smiled. The system includes two larger orange K-type stars, Alpha and Beta Centauri, orbiting fairly close to each other, with a third smaller companion, an M-type red dwarf star dubbed Proxima Centauri, which is in fact our closest neighbor, at 4.25 light-years away. It is 8 times lighter than our Sun, and its luminosity is a tiny fraction of our star. Luckily, it is a stable red dwarf. Thus, it was the subject of many astronomical observations aimed at planets, which began as early as 1970s. It was the 2013 to 2016 period which brought success, and the planet now known as Proxima Centauri b was found via observations. It orbits its tiny star at about 7.5 million kilometers away from the star, so effectively 20 times closer than the Earth is to the Sun, with its orbital period, or a year, lasting only 11.2 Earth days. Its mass is slightly higher than that of our planet. The best news, though, is the fact that Proxima Centauri b may actually lie within the habitable zone of its host star. Other than that, the planet seems to be of similar core composition to the Earth, but contains less water. The main issue with this planet is the fact that it is tidally locked with the star, not unlike the Moon and the Earth. This means that the same side of the planet faces Proxima Centauri at all times, which means that most of the planet has extreme conditions precluding the existence of life as we know it. Still, the planet receives about 65% of the radiation the Earth does, and the equilibrium temperature on it might be about -40 degrees Celsius or Fahrenheit, just about enough for life to possibly develop. The twilight zone, running like a ring around the planet between the eternal day and the eternal night sides of it, would be the area possibly supporting life. The possible atmosphere of the planet would likely contain oxygen and carbon dioxide. The issue here is the still high UV and X-ray radiation levels coming off Proxima Centauri, much higher than on the Earth, forcing any life forms present there to adapt accordingly. Unfortunately, due to the distance and difficulties involved with exoplanet observations, there is a lot of gases involved, and the parameter ranges are broad enough to both render any conclusions tentative at best and fuel the search for more detailed data, and thus answers regarding Proxima Centauri b. This planet is not the only one around the Proxima Centauri star. There is also the planet known as C, which is a super-Earth or a giant Earth-like planet or a gas dwarf. It is likely surrounded by a vast and extensive system of rings, possibly as impressive as that of Saturn. The planet is very cold, with temperatures reaching well below -200 degrees Celsius. The other planet, known as D, is a sub-Earth type planet, with its mass above 1/4 of the Earth, and it orbits close to its star, at 4.3 million kilometers, with the year there lasting just over 5 Earth days. It is also likely tidally locked with its planet, and much hotter than planet B, with surface temperatures being likely close to the boiling point of water. For these reasons, both planets C and D are not very likely candidates for life habitats, but they are still interesting in their own right. It would seem that planetary systems are rife in the cosmos, as our second nearest neighbor, the Barnard star, currently at a distance of nearly 6 light-years away, also hosts a planetary system. This star, which is the fastest moving star in relation to the Sun, has a system consisting of 4 planets designated as D, B, C, and E, in order of their increasing distance from the host star. These planets are much smaller than the Earth, between 20 and 33% of our planet's radius. That fact alone would not preclude life. However, Barnard's star is an example of a red dwarf M-type star which emits massive solar flares, ejected with enormous levels of radiation, enough to effectively wipe out any life existing on the Earth, for example. Therefore, Barnard's star is not considered to be a likely candidate for life as we know it. We will continue our look for the next closest candidate for possible life as we moved outwards from the Sun. Stars like Wolf 359 and smaller brown dwarfs have no planetary companions, either found or confirmed, around them. The exception is the Lalande 21185 star system, which thus far has 2 confirmed planets, but they lie outside the habitable zone of the star. The other planetless systems are also joined by the brightest star in our sky, Sirius A, which only has a dim white dwarf, so effectively a dead star, called Sirius B, as its companion. The next potential star which could host life lies at a distance of 10.5 light-years away from the Sun. It is an orange dwarf star of the K-type, visible in the southern hemisphere with the naked eye. It is a very young star by stellar standards, especially of orange dwarfs, and it has formed just short of 1 billion years ago, which could correspond to the age of unicellular organisms on the Earth. The name of the star is Epsilon Eridani, and the star itself is just 20% smaller and slightly colder than the Sun. In the 1980s and 1990s, first a dust disk was observed around the stars, followed by the disk asymmetry, all pointing to the presence of a planetary system. By now we know that the system includes one and possibly two planets, two asteroid belts, and one main dust belt around the star. The planet, dubbed Epsilon Eridani b, or Aegir, is an excellent match to our own Jupiter in terms of the size and its orbit, and it received its name in 2015 after the Nordic god of the seas. The planet orbits its star at a distance of 3.5 astronomical units, so 520 million kilometers. Its year, or a period of rotation around the star, is 7.33 years. Similar to Jupiter, it is fairly unlikely that the planet itself harbors life, except perhaps some layers of its atmosphere. The big question is whether the planet has any exomoons around it, where life could possibly exist, similar to the oceans of Europa, for example. Our next hope for life or habitability does not lie much further away. 11.13 light-years away from the Earth, there is a quiet red dwarf star named Ross 128 in the constellation Virgo. The star does emit radiation flares, however they are relatively mild compared to many M-type dwarfs. Most importantly, it does have a planetary companion, named Ross 128b, detected in 2017. Its mass is at least 1.4 times the mass of the Earth and probably closer to 1.8 times the mass of the Earth. As is the general case with red dwarf star systems, the planet orbits close to the star, and the year on Ross 128b lasts just short of 10 Earth days. The planet is most likely tidally locked, with one side having an eternal day while the other has an eternal night. At a distance of about 7.5 million kilometers from the star, it lies just about the inner edge of the habitable zone, and at least in theory could offer conditions for life in the twilight strip running around the planet. As a curiosity, a radio signal was detected from Ross 128 in the spring of 2017, but as the star was passing through the plane in which man-made satellites orbit, this detection was most likely a radio interference from one such object. The next potential location for life is 11.5 light-years away from the Earth. The binary star system, known as Struve 2398 or Gliese 725, located in the constellation of Draco, is a pair of small red dwarf stars. The one designated as A has a super-Earth planet discovered in 2024, but the planet orbits very close to the star, too close to be in the habitable zone. The B member of the stellar pair has a so-called super-Earth planet, estimated to have the mass of 3.4 times of the Earth, and orbits the parent star with a cycle of almost 38 days. This planet would fall into the habitable zone of Struve 2398b and requires more detailed studies in the future. The next star is located 12 light-years away from us and can be found in the southern constellation of Cetus, the Whale. Tau Ceti has long been a potential candidate for extraterrestrial life and the subject of careful studies. It is a very stable star belonging to the same G-type as our Sun, although it is slightly smaller and dimmer than the Sun. Still, it is the star most closely resembling our Sun in our closest stellar neighborhood. Observations of Tau Ceti revealed the presence of a debris disk around the star, which is often the hallmark of a planetary system. A study from year 2012 hinted at the presence of 5 planets in this system, but these results were uncertain. This was followed by another study from 2017, which found 2 of the same planets as the 2012 study, but instead of the other two, it found two different objects possibly orbiting the star. Still, these studies mention the uncertainty of their results, and thus far all those discoveries remain unconfirmed, with each study carried on tau Ceti yielding different results. The most likely possibilities are tau Ceti e, a planet which may lie outside the habitable zone of the star, and it would be almost 4 times heavier than the Earth. The conditions on it would resemble those of our Venus, so the planet is likely too hot for life to develop. The candidate known as tau Ceti f may lie within the extended habitable zone of the star, but the status of this one is even less certain than that of tau Ceti e. Also 12 light-years away from the Earth lies the little-known star named GJ 1061, which is a red dwarf, but unlike many of such stars, it is actually stable. It is 8 times smaller than our Sun and emits only 0.2% of its light. However, it does have a planetary system discovered in 2019. It includes 3 planets designated B, C, and D in increasing distance from the star. GJ 1061d orbits the star within a possible habitable zone, while the C planet lies near the inner edge of the habitable zone. Since there are no radiation flares coming from their host star, it is possible that those planets could have actual atmospheres. Planet C could see its surface temperatures being actually very similar to Earth, with a similar atmosphere, and the temperature would be in the low 30s degrees Celsius. Planet D is colder, with temperatures dropping below minus 20 degrees Celsius or minus 10 degrees Fahrenheit, but still not outside the possibility of life to exist there. Both planets have short orbital periods or years of 12.4 and 6.7 days respectively. Planet D could escape the tidal locking we have mentioned before, which means it could also experience actual day and night cycles. 12.35 light-years away from the Sun, we have another red dwarf star, named Luyten's star. It is a star with its mass being 1/4 of our Sun and about 1/3 of its radius. In 2017, 2 planet candidates were discovered around the star, with the outer one, designated as B, being a super-Earth almost 3 times heavier than our planet and residing in the habitable zone of the star. 1 year there lasts 18.65 Earth days. It lies on the edge of habitability and would require quite a few factors weighing in, such as surface albedo or light reflectivity, and we also do not know if the planet has water of atmosphere for life to thrive, but it is certainly a candidate. The inner planet, designated as C, is one of the lightest exoplanets discovered so far, just slightly heavier than the Earth. But unfortunately, its orbit lies farther away from the habitable zone of Luyten's star, so probably no luck with finding life there. Interestingly, the Sonar Music Festival in Spain has sent a series of radio signals to the star in October 2017, making 2042 the earliest time when we could receive a radio response from Luyten's star. Another named star with an interesting planetary system is the Teegarden star. Just like the predecessor we just discussed, it is a red dwarf star, just even smaller and dimmer than Luyten's star. Its mass is just 1/10 of that of the Sun, and its luminosity is a tiny 0.1% of the Sun's. In June 2019, observations showed that there are 2 Earth-mass exoplanets orbiting that star. Planet B seems to be located within the star's habitable zone, in a position which would be located between Venus and Earth in our solar system, while planet C lies just at the outer edge of it, close to where we have Mars. Despite the location, some researchers claim that the planets have very little chance of having favorable conditions, estimated at 2 to 3%. Others say the planets could have dense and heavy atmospheres and even liquid water on their surfaces. They also receive more X-ray radiation from the star than we get here on Earth, but this effect could possibly be negated through denser atmosphere with a different composition. It's definitely an interesting system and one worth a closer look in the future. Wolf 1061, a star located in the constellation of Ophiuchus, is another red dwarf with a planetary system, at a distance of 14.1 light-years away from us. 3 planets designated as B, C, and D have been discovered around this dim red dwarf star, with masses ranging from 1.9 to 7.7 times the mass of the Earth. Planet C is the best candidate for life here, as it lies just around the inner edge of the habitable zone of the star, joining Proxima b, Ros 128b, and Luiten b as some of the most solid candidate locations for habitability in our vicinity. Planet D could theoretically be habitable, depending on the composition of its atmosphere, as it lies just outside the perfect Goldilocks zone, opening a window of opportunity for life. A red dwarf star, and a fairly big one for such an object, named Gliese 687, is located almost 15 light-years away from us, and it does have a planetary companion designated as Gliese 687b. It is a planet with over 18th Earth masses and would be comparable to our Neptune. Its year would last just over 38 days, and the planet seems to be located within the habitable zone. Once again, and similar to Neptune, a lot would depend on any possible exomoons present around the planet, where life could find a niche solid enough to maintain a stable presence of some sort. Unfortunately, the system is not as well studied as Ros 128, for example. Our next stop is 15.2 light-years away from the Earth in the constellation Aquarius. There we can find the closest planetary system to us with more than 2 fully confirmed planets, Gliese 876. The star itself is a red dwarf with approximately 1/3 of the Sun's radius and mass, with 1.3% of its luminosity. So far we have 4 planets confirmed around the star, D, C, B, and E, arranged according to the increasing distance from the star. Those planets vary, with planet C being smaller than the Earth and planet E being a Neptune-sized one. Planet D may be a very dense and rocky body. Planet C seems to be located within the habitable zone of its star, and it is relatively likely to have liquid water, or even more so, on the surface of its moons, if any are there. The planet itself may also be composed of gas, which renders life more difficult, but also does not entirely exclude such a possibility. The satellites of planet B could also be located well enough to have liquid water, one of the most important components required for life. Gliese 752 is a binary star system located just over 19 light-years away from the Earth. This system includes 2 suns, the larger of which, designated as A, has the mass and radius approximately 1/3 that of the Sun, and its luminosity is 3.3% of the Sun. The star has a detected companion, which seems to be a planet with its minimum mass comparable to that of Neptune, and its orbit lies partially within the habitable zone. Perhaps its moons could harbor life, but so far exomoons are a very difficult object and subject to study. 82G Eridani at 19.7 light-years is the last star within the 20 light-year radius we are going to visit. It is important as it is another G-type star, so a yellow dwarf like our Sun, just a touch smaller and dimmer. It is also approximately 1 billion years older than the Sun. So far, observations showed the presence of 3 planets and a planetary dust disk around this star. The mass range of the discovered planets varies from just over 2 to nearly 6 times that of the Earth, placing them in the so-called super-Earth category. Other candidates for planets have not been confirmed so far. Planet D of this system is possibly a rocky body, with its mass being at least 5 and likely around 6 times that of our own earthly home. As its orbit lies partially within the habitable zone of the star, it could offer conditions for life as we know it, depending on its exact composition. Another option for this planet could be a tiny gas giant rather than a rocky body. With its orbit partially out of the habitable zone, it is not inconceivable for any potential life present here to fall into hibernation, as at the farthest distance away from the star, the temperatures on the planet would be low enough for water to freeze. There are other stars with possibly habitable planets within the closest 20 light-years radius from us, but those require more detailed studies to say anything more conclusive about any possible planetary companions. But we can look a bit farther away from home, and it seems the distance is definitely not a limitation to finding places where native life could exist, or where our own future colonies could find a friendly territory to settle in. 23.6 light-years away, in the constellation of Scorpius, we have the star system known as Gliese 667. It is a triple star system, just like the Alpha, Beta and Proxima Centauri system we started our interstellar journey with. And just like in the Centauri system, star C, where our interesting planet is the smallest of the three stellar components of the system. Its planet, designated as C, is a super-Earth, much heavier than our home, just over 4 times. Its equilibrium temperature is only around 4 degrees Celsius or 7 to 8 degrees Fahrenheit above the freezing point of water, which is not the worst starting point for life similar for that on the Earth. Overall, the planet could actually be a little warmer than the Earth depending on the atmosphere, as it does seem to receive more radiation overall from the star compared to that we do from the Sun. Given the longevity of the host star, which could be anywhere between 100 and 150 billion years, potential life on Gliese 667 cc would have enormous amounts of time to develop and flourish. The drawback of this planet's location, similar to what we have already discussed for other red dwarf star planets, would be the tidal lock, limiting the best areas for possible life to a thin line running around the planet. This area could be expanded if the atmosphere had good heat transfer properties. Nevertheless, these are substantial limitations in this particular case. Following the trend of red dwarf stars, we have Wolf 1069, located 31.2 light-years away from us. It has 17% of the mass of the Sun and 18% of its radius. The star is relatively quiet for a red dwarf, which is definitely a bonus. Its planet, Wolf 1069b, is located within the conservative habitable zone of the star, and it has a mass similar to that of the Earth. It receives 65% of the amount of radiation that the Earth does, and its equilibrium temperature would fall just below -20 degrees Celsius. While these are not the perfect conditions, this is not the worst candidate for a place to live either, and could possibly become an interstellar colony at some point. As is the case with most red dwarf star planets, this one is also tidally locked, with eternal day and eternal night on the respective halves of the planet. A bright red dwarf star with the name of L9859, located 34.6 light-years away in the constellation of Volans, is another interesting location. This small star has at least 5 and possibly 6 planets orbiting around it. The two innermost planets, B and C, as well as planet E, are rocky bodies similar to places like Mercury. Planet D has a strikingly low density, indicating amounts of water so high that even up to 30% of the planet's surface could be covered in water, and this means oceans. It is also possible that this planet has atmosphere rich in sulfur compounds, and this is an element which is one of the ingredients for life. The orbital period, or 1 year, on L9859d lasts 7.5 days, and the planet is about 1.6 times the mass and the size of the Earth. Now we are going to visit a true gem of the world of exoplanets, the 55 Cancri system. It is a binary star system located in the constellation of Cancer at 41 light-years away from us. It consists of two stars. The main one, 55 Cancri A, is an orange K-type dwarf, while the smaller one is a red dwarf. It's not the worst starting point for life. The A component of the binary star system is known to have 4 confirmed planets and 2 unconfirmed planet candidates. The confirmed planets were named after astronomers: Galileo, Brahe, Janssen and Harriot. The smaller component of the binary star system, 55 Cancri B, has 2 exoplanets with less poetic designations BB and BC. The planets orbiting 55 Cancri A began being discovered as early as 1997, while 55 Cancri B had to wait for the discovery of its 2 companions all the way until 2025. All the planets of the A star are massive, at least falling into the super-Earth category, while most likely they are even as big as our own gas giant planets. Planet F, named Harriot, lies on the edge of the habitable zone, and with its size it is difficult to tell whether it would even have conditions suitable for life, similar to that present on the Earth. Following such a heavy hitter as 55 Cancri, we have one of the best studied exoplanet systems to date, TRAPPIST-1. The star is known as an ultra-cool red dwarf, and it is located 40.66 light-years away from the Earth. It is a really tiny star. It is just slightly larger than Jupiter, with a mass of 9% of the Sun. It falls at the tail end of the actual star spectrum, close to the borderline between stars and brown dwarfs. And this system was the subject of observations in 2016 and 2017, with the first observation showing the presence of 2 planets, followed by 5 more in the second study, up to the total of 7. The planets hold letter designations from B to H, and as we move outwards and away from TRAPPIST-1. The entire system is tiny though, as the orbits of all the planets would fall within the orbit of Mercury, our innermost planet of the solar system. This is not too surprising given the size of the host star though. All the planets discovered in this planetary system show tentative compositions similar to that of the Earth, with the difference being either a smaller ratio of iron in their cores or higher percentages of volatile compounds. These results have high uncertainties though. It is quite likely that the planets could have liquid water, possibly even existing as rivers and oceans. Planets D, E, and F, or E, F, and G, depending on the calculations, fall within the habitable zone of the star, which makes their number the highest of all known extrasolar systems where life could exist, at least theoretically. We cannot entirely predict whether water actually flows on those planets, as that also depends on factors such as atmosphere presence and its composition, and the reflectivity of the planetary surface, possible dynamics of water and ice, and so on. We can say though that to the best of our knowledge and ability, those planets do not have moons, and thus no tidal phenomena like those caused by the moon on Earth. All in all, the system as a whole is quite complex, and would warrant a video of its own to describe it in detail. The last of the star systems we are going to look at in more detail is called LHS 1140. It is yet another red dwarf star located in the constellation of Cetus. The distance to the star from the Sun is almost 49 light-years away. The star has 18% the mass of the Sun and 25% of its radius. Currently, it is known to provide home for 2 planets found around it. The inner one is known as LHS 1140c, and it is a rocky body located too close to the parent star to harbor life as we know it. It's simply too hot there. The outer planet, LHS 1140b, is a different story. This planet lies right bang in the middle of the habitable zone of the star. It is known as super-Earth with mass about 5.6 times that of our own planet. It receives almost half of the light we get from the Sun. What is most important though is the detected presence of 9 to 19% of the planet's mass consisting of water. This indicates the presence of massive oceans on the planet, and this could offer a possibility of life developing in abundance in such an environment. A lot depends on the exact conditions on the planet though. Depending on its albedo or the ability to reflect light, it could be anywhere between 25 and 50 degrees Kelvin lower than on the Earth. But if the planet has a fairly dense atmosphere, which is likely given its mass, the temperature could be just about 10 to 12 degrees lower than ours. This is close enough for life to exist. If the greenhouse effect is twice as strong as it is for us, the temperature on the surface would be about 20 degrees Celsius or 68 degrees Fahrenheit, making it a perfectly comfortable place for life. Needless to say, it is one of the most interesting candidates for habitability in relative proximity of our home. Now, we have not really exhausted the list of habitable planets in the near vicinity, and 50 light-years away is barely a step outside our doorstep. The galaxy itself is thousands of light-years in diameter, so it is easy to imagine how many possible worlds where life, alien or our own, could live and quite possibly thrive. In part 3 of this video, we are going to take a look at technology bypassing the limitations for humans and their ability to live elsewhere. For now, we already know that humans are capable of living off Earth. Every single day we have astronauts residing on board the International Space Station, for example. This means that we are able to provide the capacity for life and residence in space. This also offers ample opportunities for studying plant growth, with the aim of growing food independently, studying the impact of low gravity conditions on human health, and so on. The main issues underlying humanity setting up a possible base, most likely initially on the Moon, followed by Mars, lie with simple things we need to exist. Oxygen is the first one of those. It would require a closed system of some kind, where oxygen could be brought over from the Earth or obtained locally, for example from rocks, as well as a purification system converting exhaled CO2 back into oxygen. Plants grown inside such a habitat would be an amazing opportunity of using said carbon dioxide and turning it into food and oxygen, thinking longer term. This, of course, would require artificial light most likely, tailored to provide conditions similar to those on the Earth. The next problem lies with the atmosphere. The Earth is the only place in our solar system suitable for breathing, and any colony would require an artificial atmosphere. If a colony was to exist long term, we would also have to think about terraforming. That is, conversion of the native surface of the Moon, other moons or planets into soil. This is tied in with the presence of enough water for plants grown by the colony, and for humans too. Polar caps present on Mars could be a good starting point. All of this shows how fragile our human condition really is, and how many hurdles we would have to go through to exist in places other than the Earth. When it comes to otherworldly life, and here we will limit our considerations to intelligent alien species, it is convenient to assume that such species would far exceed our own technological capacity, and this leads us to various possibilities of life and habitats. First, we have spaceships. Assuming here that UFO sightings include actual spacecraft, it seems that visiting the Earth from elsewhere poses little to no issue in itself. This also indicates that the interior of the craft is providing the suitable atmosphere and sustenance, in the forms required by such non-human beings. Given the size of such ships, it is also easy to assume that those are more of a small craft rather than full-scale missions. Therefore, it is not inconceivable to imagine bigger motherships, where complex systems enabling interstellar travelers provide them not just with the most basic of necessities for life, but could offer other options as well. From leisure to even states of deep stasis, for example low-temperature biostasis, enabling the passengers to pass even years while their bodies could remain virtually unaged. Then we have the point of origin of such alien species. The safest assumption would be aliens living around the dwarf star, from A-type to M-type, among those listed before most likely. But they could just as well inhabit colder objects, such as brown dwarfs, white dwarfs which are stellar remnants, or even really exotic locations, such as the areas near the borderlines of black holes. Civilizations higher on the Kardashev scale could build gigantic structures, from artificial habitats we can already imagine, at least in theory, like slowly spinning rings surrounding planets, which provide artificial gravity thanks to their spin, and could easily host tens of thousands of inhabitants at once. An expansion of such concept lies in Dyson spheres or swarms, a myriad of objects surrounding their host star, drawing a big part of its radiated energy and converting it for almost any imaginable purpose, from photosynthesis to powering amazing feats of technology we can only dream about now in the 2020s. An extreme version of this concept is the so-called Matryoshka sphere, which is basically a reflection of the Russian nested dolls, one inside another. If a civilization would be capable of building one Dyson sphere within another, they could provide habitats for enormous amounts of beings, aliens basically, reaching billions if not trillions, with relative ease, given that they would be drawing the entire energy radiated by the star, or at least a very big part of it. A sufficiently advanced civilization could actually form a stellar vehicle this way, and somehow guide the entire star, drawing energy from it when necessary, as well as harvesting mass and releasing it to the star to provide it with an extra boost of energy. The possibilities are almost endless here, and I think that we can really imagine only civilizations of Kardashev Type 1 and Type 2. Type 3, which would be able to harness the energy of an entire galaxy, could use almost anything to live and travel, including the most exotic and bizarre places. There already exist notions of black holes providing their own habitability zones, located relatively close to the event horizon or the boundary beyond which nothing can escape gravity anymore, but far enough to remain stable. If Hawking radiation is true, which means that the black hole ejects approximately half of the mass it consumes, such a civilization would receive another boost of energy, and the black hole is an enormous energy source we can barely comprehend. The same goes for quasars, or active galactic nuclei, which are basically gigantic black holes, ejecting streams of energy and particles at a speed nearly that of light, offering a boundless source of energy. And even considering the darker future of the cosmos, past the era of the stars, such civilizations would be capable of existing orders of magnitude longer in terms of time than any life as we currently know. Perhaps a civilization which emerged, let's say 10 billion years ago, is already capable of something like this. Such beings could be considered virtually immortal as a whole, as black holes are predicted to exist for at least 10 to the power of 60 and even as long as 10 to the power of 100 years. So, in this special video we took a brief look at how and where life could exist, from the comfortable closeness of the Earth to the far reaches of the cosmos and the depths of time. I hope it provided a spark igniting some curiosity and thought as to the miracle of existence we all experience, but rarely give a deeper thought to in our daily lives. If you would like to share your thoughts, comments, perhaps if you wish to see a video speaking about something specific and related in more detail, let me know in the comment section down below. Thank you so much for watching and all the support for the channel, it means a lot to me. Like and subscribe if you enjoyed the content, and I will see you soon in another video. Take care.